Hi there. Now in the last video we have looked at the cases when we need to avoid recursion and when we need to use it. Now in this lecture we will look at how to write recursion method for any given problem in 3 steps. We have learned from previous lecture that a recursion function calls itself repeatedly until base condition is satisfied. A function calling itself is very dangerous, as it is relatively less intuitive and may run into some runtime error if we don't treat it with extreme caution. So here I will introduce you a 3-step approach that can make you confident enough to write your own bugless recursive function. So as an example, I'll use a mathematical problem which is called factorial. Now in case you don't know what is factorial, let me just give you a brief explanation. Factorials were used to count permutation at least as early as the 12th century by Indian scholars. It's a product of all positive integers less than or equal to n, denoted by n and exclamation mark. This donation introduced by French mathematician Christian Kramp in 1808, and it's only calculated for positive integer numbers, and the factorial of 0 is 1. As an example, if you want to calculate a factorial of 4, the answer will be like this. So we multiply 4 with 3 and 3 with 2 and 1. So the multiplication starts from 4 until we reach the 0, but 0 is not included over here. So in our case n is 4 and all positive integers less than or equal to 4 are 4, 3, 2 and 1. Now let's see another example. Let's say if you want to find the factorial of 10, so how do we do that? Again we start from the 10 and take all positive numbers that are less or equal to 10, which are 10, 9, 8 and it continues until 1. So if we multiply this number, we get this number over here. So based on these points and examples that we mentioned over here, we can express factorials of n like this. So n multiply with n minus 1, multiply n minus 2 until we reach the 1. Now let's see how can we find out this factorial of any given value using a recursive method in 3 steps. So the first step is recursive case, the flow. First we need to identify the recursive case, which is how a factorial function is defined using factorial functions. So we can identify that using general expression for factorial like this. So we can write that factorial of n is equal to this equation, as we identified in previous slide. So the question over here is, how can we rewrite this recursive function to have factorial on both left and right side of this equation? So if we look at this equation carefully, we can see that this part over here can be written n minus 1 factorial. So if this part is not clear, let's calculate the n minus 1 factorial. So if we calculate n minus 1 factorial, it is n minus 1 multiplied with n minus 1 minus 1 multiply with n minus 1 minus 2 and it continues like this. So here n minus 1 remains n minus 1 and n minus 1 minus 1 it's n minus 2 and then n minus 3 and it continues until 1. So this means that this equation over here can be written like this. n factorial equals to n multiplied with n minus 1 factorial. Now with this we have identified our recursive case. Now I'm going to show you the steps one by one in Java also, so let's switch to our Java editor and write a simple function which includes this recursive case. So here I'm using a website called Replit. So here it provides several editors for different programming languages. So in our case I'm using it for Java. So the first thing that we are going to do, we will create a simple function, and this function will take as a parameter n, and which will return n multiplied with factorial of n. So I'm going to write our function inside this main class. So I will declare function like this, public int. So it's going to return integer, that's why I'm putting int over here, and the function name will be factorial, and it take as a parameter integer n. Then it's going to return n multiply with factorial n minus 1. So this is our recursive case. So as it's shown in the equation over here, we can write this equation to this function over here like this. So as you can see, we have just identified the recursive case in Java. So in this code, you can see that factorial calculation is almost done. So you might be thinking that this function over here is enough to calculate factorial. But there's a bug in this code. So because if you run this function for example, factorial 3, you will see what's going on. So to see what's going on, I will print out n before this return statement over here. So to print out n, I will call system.out.println So here I'm going to print n to see how this is calling n. And inside this main function, we are going to call our function. So to call it, I need to create an instance of main class. So I will create it like this, new. So I will put R over here, which stands for recursion. So I will call new main. Then here we can call our function. So here I will create another variable. So let me just put over here the name of class recursion. So here I can create value rec, which equals to recursion dot factorial with the parameter of 3. So here I need to put this one over here, and then I will print out this rec value. So I will just copy the code from here and put it over here to print out this one. So let's run our code to see what's happening when we run this code and what's bugged inside this code. So if I click just run over here, so you see that our function get called infinitely. So when it reaches the end of the limitation, it says that exit starts with 1. So this means that our function called itself infinitely. From here, we can clearly see that the function keeps calling itself without stopping. And this leads to system crash if we implement it in an application. So how do we prevent this case? So to prevent this case and to write bugless code, we need step 2. So in the step 2, we will learn how to prevent infinite loop in the recursion. So let's continue with the second step. So the second step is we need to create base case. It's calling the stopping criterion. So as you remember from previous lectures that we need a base case to prevent infinite loop. So here we need a base case for our recursive function where it stops calling itself. As we said in the definition of the factorial that factorial of 0 is 1. So it's obvious that the factorial of 1 is also 1. So as a base case, we can use these cases. So let's switch to our code, and before running any value, we can define the base condition over there. So as we said, our base condition is 0 factorial equals to 1 and the 1 factorial equals to 1. So based on these two cases, we can write our base condition in our code. So before calling any function recursively, here we will write an if condition, which will be the base case for us. So if n equals 0 or n equals 1, so in this case, we will stop the recursion, so we will return 1. Otherwise, we will call our method over here. So for this case, I'm going to remove this print statement from here and try to call this function one more time to see how this is working. So if I call this one, you see that. So the output for factorial 3 is 6, which means that when we multiply 3 with 2 and 1, we will receive 6 over here. So everything works okay in this case. Now you might be thinking that we are done with our code in these two steps because our codes work the way that we want. So do you think that our method over here stops for every possible argument of n? So are we sure that our function will not run forever for any n? So here I want you to pause the video and think that if there is a case that our function might call itself infinitely. Alright, hopefully you have found it. Okay, if you haven't found it, let's find it together. So let's see what's missing over here. The most important thing to consider when writing a recursive function is making sure that function stops for every possible argument of n. So to explore these cases, we have step 3. So in the step 3, the case is called unintentional case, the constraint. So we have base cases for n equals 0 and n equals 1, and our recursive case calls the function itself with argument of n minus 1. This means that function will reach as a base case only if the factorial n starts with non-negative integer n. So from definition of factorial, we know that it's calculated only for the positive number. But if someone runs this function for minus 1 or minus 2, what will happen? In these two cases, we can never reach the base condition that we declared over here. So to prevent these cases also, we need to make sure that our n is always positive integer number. So for these cases, we will prevent this. For example, if someone is calling the factorial for negative integers, then in this case, we will return minus 1. So this means that we cannot calculate it. You can return any number you want, or you can return null value. But in our case, I'm going to return minus 1. So in this case, before this base condition, I will check that if n is less than 0 or not. So if n is less than 1, then in this case I will just return -1. So if we run, for example, our function for -2, you will see that the output will be -1. So we have included all cases over here. So with this last step, we have successfully implemented recursion for factorial number. So hopefully everything is clear with this method, but to make things more clear and more understandable, let's run this function for any integer number and see what's happening behind the scene. So I've just copied this function from the previous slide to here and shown you that what's happening in the background when we call this recursive function for 4. So if our parameter is 4, the control comes to this first condition, and it checks that if the n is less than 0 or not. So we see that n is not less than 0 because in this case n is 4. Then it comes to the second controller. When it comes to the second controller, it checks that if n equals to the 0 or 1. We see that it's not equal to 0 or 1. Then it continues to the third condition. So in the third condition, we have n multiplied with factorial of n minus 1. So this means that this function will call n factorial minus 1. So in this case, n is 4 multiplied with factorial n minus 1 will be 3. Now for 3, one more time we are going to call this function. So here we are checking that if n is less than 0 or not. So we see that 3 is not less than 0. So it continues to the next if condition. So in the next if condition, we are checking that if n equals to 0 or 1. So in this case, n is 3. So it's not equal to 0 or 1. Then it continues to this expression over here. So when we call this expression, 3 multiplied with n factorial n minus 1. So n in this case is 3, so it will call n factorial 2. Now when it comes to n factorial 2, it goes one more time to this condition. So we are checking that 2 is not less than 0. Then it comes to the this if condition. Here we are checking that 2 is not equal to either 0 or 1. This means that it will go to this factorial over here. So in this case, 2 multiplied with factorial of 1. Now when it comes to factorial of 1, one more time it's going to this if condition. So it's checking this if condition. And we see that in this case, it's not less than 0. Then it comes to this if condition. So when we reach over here, we see that n equals to 1. So this means that this expression over here, factorial 1, will return 1. So if we calculate this expression, we can calculate this expression over here. So factorial 2 will be 2 multiplied with 1. So factorial 2 will be 2. So based on factorial 2, we can calculate factorial 3. So factorial 3 will be 3 multiplied with 2. So this means that it's going to be 6. Then we can calculate factorial 4 based on factorial 3. So factorial 3 is 6, and the factorial of 4 will be 4 multiplied with 6 is going to be 24. So this means that the factorial of 4 will be 24. So this is how we recursively find the factorial of any given number. And if you call this factorial function for any given number, this is what's happening in behind the scene. So if first it calls this factorial, then it calls until we reach the base condition. So when we calculate the base condition, then one by one it comes back to the final version of the factorial. So hopefully you have understood how to write a recursive method in 3 steps and how can we find the factorial using recursive method. So basically you can apply these 3 steps for any given problem that you want to solve using recursion. Now in the next lecture we will solve another problem using recursion by implementing these 3 steps over here. So see you in the next lecture.